Hey everyone, and welcome. Today, we're going to dive into a really cool classic physics experiment. We're going to measure something that seems totally invisible, the refractive index of a simple glass slab, and we'll do it using a special kind of microscope that basically acts like an incredibly precise vertical ruler. It's pretty neat. So here's our game plan. First, we'll talk about a common optical illusion that's actually the key to this whole thing. Then, we'll check out the main tool we need to do the job. After that, we'll walk through the 3 simple measurements we have to take, figure out what those numbers actually mean, and finally, put it all together to get our answer. All right, let's start with something you've definitely seen before in your everyday life. It's a little trick that Light plays on our eyes, and it's the entire reason this experiment even works. So, think about it. You ever look into a swimming pool and think, that doesn't look so deep? The bottom always seems way closer than it actually is. Well, you're not imagining it. That's a real physical effect. It happens because light bends when it goes from the water to the air before hitting your eyes. And that apparent shift in depth, that's exactly what we're going to measure today. And that brings us to the star of our show, the refractive index. We usually just call it N. All it is really is a number that tells you how much a material can bend light. And conceptually, it's super simple. It's just a ratio. You take the real depth of something and divide it by the fake, shallower depth that you see. Okay, so how on earth do you measure this illusion inside a solid piece of glass? I mean, it's not like you can just stick a ruler in there, right? Nope. We need a special instrument that's built for making these kinds of super precise vertical measurements. For this whole setup, our toolkit is pretty focused. We need the main event, the traveling microscope, we obviously need the glass slabs we're testing, and we need some kind of really fine dust. Lycopodium powder is perfect, which will help us get a sharp focus on the top surface of the glass. Okay, so this is the key piece of equipment right here. The best way to think about the traveling microscope isn't as something for making things look huge. Instead, think of it as a super accurate, movable eyeball that's attached to a vertical ruler. Its whole job is to let us focus on different levels, the very bottom, the illusion, and the top, and tell us the exact height of each one with amazing precision. So, here's where it all comes together. The entire experiment, seriously, just boils down to taking 3 specific readings. All we're doing is going on a little vertical journey with our microscope, and we're just going to make 3 important stops along the way. So here's how we do it. First, we put a tiny ink cross on the base of the microscope and focus on that. That's our starting point, our baseline, and we call it reading R1. Simple. Next, we put our glass slab right on top of that cross. Now the cross looks closer, so we have to raise the microscope up to get it back in focus. That new position, that's the illusion, and that's reading R2. And finally, we sprinkle a little of that fine powder on the top surface of the glass and raise the microscope one last time until the powder is crystal clear. That gives us the position of the very top, our reading R3. And that's it. Okay, so we've got our 3 numbers, R1, R2, and R3. But right now, they're just positions on a scale. They don't mean a whole lot by themselves. So let's see how we can translate these raw readings into the real-world properties we actually need. Just to remind ourselves of the core idea, right? The refractive index N is just the real thickness divided by the apparent thickness. And believe it or not, our 3 little readings contain all the information we need to find both of those values. So, this is how we do it. This is the practical formula. N equals R3 minus R1 divided by R3 minus R2. Now, I know it looks like a bit of math, but let's break down exactly what those 2 parts of the fraction actually are. It's really clever. Here's the logic. The real, actual thickness of the slab is just the distance from its top surface, which was R3, all the way down to the bottom mark, which was R1. So R3 minus R1. Makes sense. Now, the apparent thickness is the distance from that same top surface, R3, down to where the mark appeared to be, which was R2. So R3 minus R2. See? These simple subtractions give us the exact values we need for our ratio. All right, enough theory. Let's put this into practice with some actual numbers. We're going to look at a sample data table from an experiment with 3 different glass slabs and just see this formula in action. Okay, check this out. For that first slab, we subtract R1 from R3 to get a real thickness of 1.820 centimeters. Then we subtract R2 from R3 to get an apparent thickness of 1.215 centimeters. Divide those 2 numbers and bam, we get a refractive index of about 1.5. And what's really amazing is, even though the other slabs have different thicknesses, that final number for N, it stays incredibly close, just hovering right around that same value every time. So, to get our most accurate and final answer, we just take the average of all our results. And in this case, the mean refractive index works out to be 1.52. That's it. That is a fundamental characteristic value for this type of glass. We've actually measured an intrinsic property of the material itself. And that's really the big takeaway here. This is not a coincidence. This specific ratio of our measurements is always going to be a constant for a given material because it reveals something fundamental about it. It's such a beautifully simple way to put a number on how that material bends light. Now, to get a really clean result like this, you got to be careful about a few things. First, you have to get rid of something called parallax error, basically making sure your eye and the crosshairs move as one. Second, to avoid any slack in the focusing knob, you should always make your final focus adjustment by moving the microscope upwards. And of course, the whole setup needs to be perfectly level. So we've totally nailed how to measure a solid. But that leaves us with a really fun question to think about. This whole method is based on that vertical journey through different layers. So how could you tweak this exact procedure, maybe with a small container, to apply the very same principle to find the refractive index of water or oil or any other clear liquid? Something to chew on.